Hello and welcome to another video. In this one, we're going to show you how I debugged a memory leak in a production application at Sentry. I initially thought it was a memory leak in Postgres itself, but it ended up being in krb5, which is an authentication, something like basically everything uses krb5 in some way or another. And I found a memory leak in it, and I'll show you how I found it and what tools I use, and eventually how I fixed the bug. But anyway, let's jump into it. All right, so in order to set the stage, we got to run a worker, a real production worker, but we're going to run it locally. This is a Celery worker. If you're familiar with Celery, it's sort of a task queue management thingy. You can't see this over here, but it's max tasks per child. I'm basically just setting that to a really large number because we want to profile the process. We don't want it to restart on us, so just keep running forever, basically. We're also doing concurrency 1 because we want to trace a single process and not bother with all the other ones. This will still fork a child, and so we'll have to manage that. But let's run this. I have another script which feeds data into this. It's not really important what it does, but it is basically just sending data into there. This incr function eventually calls the Celery task and defers its work. Sentry exec t.py. Let me make sure that this started. Yeah, there's all sorts of warnings. We need to change our Celery settings, actually. I think Celery is broken. Celery is doing it wrong, but whatever. That's neither here nor there. Okay, anyway, we're running the worker. We're feeding data into it. And I noticed when I looked in htop at these particular processes, you'll see here we have, this is the parent process, this 250 meg. And this is the child process. And you'll notice that the resident memory is creeping up over time. And so I was like, oh, okay, cool. We've reproduced the memory leak. That's exciting in its own. Pretty often you chase these bugs in prod, never find them in dev. So I was already excited when I got to this point. But I'm going to show you how I used a tool that I had not used before and sort of learned how to use in order to reproduce this. And that tool is called memray. Memray is a memory profiler. It's from Bloomberg. Some of my buddies actually worked on it, so that's kind of cool. But basically, you can attach it to running processes, or you can wrap processes, and it'll look at allocations in them. So I'm going to show you the commands and how I learned to use the tool from failing at the commands over time. So the first thing that I'm going to do is I'm going to run a specific chunk of time for this worker and then stop it after that. And I did this mostly to make sure things were normalized because I was actually comparing 310 and 311 for an unrelated thing. And so I'm going to use the timeout command in order to do that. I actually did a video on timeout, so I think I did. I'll try and link that if I made a video. But basically I'm saying send SIGINT after 10 seconds, and then it will run some other process. The process we're going to run is memray run. And I'm just going to do it with no arguments, which is, well, I'm going to do it with quiet. We'll show you that one argument. Otherwise, memray runs an in process, like a foreground top-like thing, which I didn't find super useful personally. I found it a little bit overwhelming and difficult to read, but we'll get to the parts that I think are important. This is actually the wrong command, and the hint about Celery forking will come up later. But after that, you just pass in your command that you want to run. So Sentry run worker queues counters blah blah blah, the same command as before. This is going to run for 10 seconds, and it's going to profile all of the allocations in the program. We're then going to be able to generate some HTML output from memray and basically see what happened there. And so the command for that is memray flame graph. And this has a bunch of options. We're specifically looking at the leaks option because we want to know what memory leaks happened here. We do leaks, and then we can pass in our memray binary format that we got out. So that's what this memray sentry blah 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 .bin is. This will do crunch some numbers and spit out an HTML file. I actually need to download that so I can view it on this computer. And if we open that up, memray gives us a nice pretty, don't need the rest of these things here. Let's look at this one. So memray gives us a nice pretty graph of all of the memory allocations here. And I actually noticed two things went wrong when I did this first time. First, they give you a nice helpful warning up at the top that we are using PyMalloc. And without going too much into detail, PyMalloc is a block allocator and doesn't really play super nicely with normal memory profilers. You can, of course, force it to use malloc, and we will do that. Or you can use the trace Python allocators. I found that both of these work pretty well, but we're actually going to use this one because it'll help us profile native functions later. I think they both do basically the same thing. But the other thing that I noticed is this is the parent process. This is not the child process. So this is not actually what we want to profile. And so we kind of had two problems there. So let's fix both of those at the same time. Go back to our little timeout command here. And we're going to put Python malloc equals malloc. Actually, first we're going to delete all of the memory files. So I don't, first time I went through these, I got really confused by all the files that were there. I'm going to delete those. So this time, oops, run here. We're going to set Python malloc equals malloc. This forces Python to use just normal glibc malloc instead of its own memory allocator. And the other thing we're going to do is we're going to set follow forks down here. This is going to make memray follow any subprocesses that are created, or forked process in this case. And it'll generate a little binary file for every single one in those forks. Okay, so let's run this again. Memray, oh, what is follow fork, not follow forks. Oops. I'm pretty sure that's how it works. All right, so this will run again. It'll profile all of the processes and all of the child processes and spit out a bunch of binary files. And so if we look here, we should get a bunch of memray, sentry, blah, blah, blah. And the one we're particularly looking for, I happen to know, is the largest PID that we get here, which is this one here. And so we're going to do memray flame graph leaks on this guy. And that will generate a new flame graph. Takes a little bit, but it's going through a whole bunch of data, so it doesn't surprise me. Let's download that and open it again. And this told me a few things. So there's a lot going on here, but some of it is unimportant. This is some thread, some background thread, probably inherited from the parent process. And actually, I'm pretty sure this is Sentry itself tracing this, the SDK. And the actual code that we care about is in the, I want to say it's in this work loop here. Nope, not that one. Here's the actual leak that I noticed. Huh, maybe I need to run more. Hold on, I will just find the the particular one, because this actually isn't, this doesn't actually show the leak here. Maybe I didn't run it for long enough. The data feeder was running. All right, we'll run it for a little bit longer. Timeout. Man, this worked so well the first time I demoed it. But then my power went out, so we're getting round 2. All right, let's do this again. So generating our little graph. While this is generating, basically what I ended up doing is finding a particular Python call that was the leakiest one. Memray flame graph leaks. And I took that that particular function call, isolated it to its own function, and so we'll show that next. Generate. Oh, this one's taking a little bit longer. Okay, so I think this will probably give us a better result here. Surely. Okay, now that's completed. We'll download it again. We'll open it up. And no, this is still the Redis connection. Dang it. Oh, I remember what this is. There's another thing that's leaking that's not the one I'm tracing here. Anyway, I will skip this for now, and I'll just show you, I'll just tell you what happened here. Here is actually the leaky tree, this one right here. The SQL connection. Somewhere in here. Anyway, basically found that Postgres was connecting and leaking memory. And so what I did is I isolated that to its own little function. So if we cd into example Postgres by itself, and we have this little function here, which is connecting to Postgres. All it does is connect and close. So it shouldn't leak any memory. We're creating a connection and then immediately closing the connection. So Python malloc equals malloc, same thing as before. And if we run this Python file, should generate a new profile. And this will show us where the leak happens. But unfortunately, this is not going to show us much. It's just going to show us that connect is leaking. And so I'll show you the next piece of the puzzle after this one runs. We're going to decrease the number of iterations here just for the sake of the video. It's easier to show the memory ticking up over time with 10,000 iterations, but 1,000 should be plenty for us to demo this. And if we do memray flake graph leaks, oh dang it, we generated 2 of these. We generate another flame graph. Move that down there so that I can just rerun this scp command. And we'll notice that there's a leak in Postgres Connect. Now, this doesn't really show us much. This is the imports over here, so they're taking some memory, and then this is the actual execution where Connect takes a bunch of memory. Now, this doesn't tell us much, and so I wanted to dig further into this. And fortunately, memray has a helpful utility for profiling all functions, including C functions, by just passing native to the run command. Native. And so this will profile all C functions. It works a lot better if you compile your Python with debug mode and have symbols and all sorts of stuff. And we'll actually see that, that this doesn't generate the best symbol output, and I end up figuring it out in a different way later. Memray T481. No symbol information. Yep, that's fine. And we'll do that. We will download again, and then we will open it up. 8.1. And we get a whole bunch more information here. All of the C functions. Well, not all of the C functions, but a good chunk of them. This part isn't the interesting part here. This is the imports over here. This is the actual connect. And you'll notice we have a bunch of calls here, including pqconnectdb. This is basically the Postgres connection. But all of them are leaking memory in this unknown function. And that unknown function is called by getPrimaryName. And so that's probably what we're looking for. I noticed at this point that getPrimaryName, actually this is really small for you, so let's make it bigger. GetPrimaryName was called by krb5, which I knew was krb5, which is an MIT library. And so I knew that that was probably where I wanted to look for this, and that it probably wasn't in Postgres. However, by this time, I had actually reported this bug to PsychoPG2, which is the Postgres bindings that I was using, because I hadn't gone this far and figured this much out yet. I gave them a nice little minimal reproduction and showed memory leaking and that it came from this function. Ended up digging further and jumped into the Kerberos code. And in order to do that, I actually wrote a little C code. I copied the code out of Postgres to kind of demo this. Example C code. And basically, Postgres calls this GSS acquire cred to see if credentials exist at all. On my machine, they always failed, so it was always in this case. But that's not super important to this. Basically, I called this GSS acquire thread. And if we looked at Firefox here, that's this GSS acquire thread here, acquire cred. I didn't get the rest of this stuff, but we got to that later. So compiling this function, or this code, show you my little compilation. Basically just using the homebrew version of this, version 1.21.2. If you watch this video in the future, this is already fixed, so you probably won't see this problem anymore. On newer versions of krb5, I don't know that it's gotten released yet. But if we run this program, all it does is it tries that 10 times and prints this out. Not super useful on its own, but we're going to use a macOS tool called Leaks. And this is kind of like Valgrind, but it's macOS specific and it ships with the developer tools. And so if we run this, it spits out a whole bunch of garbage. You can ignore everything down at the bottom. The important stuff is somewhere up here. There's like a stack of leaks that it prints out. Yeah, here we go. So there's 2 stacks of leaks that happen here. One of them is then this function here, which is not actually important. The way krb5 has error messages is it basically has a global variable where it stores the last error that occurred. This is not actually a memory, well, I mean, it is a memory leak, but it's not actually an important memory leak because it only leaks once and it's meant to be, so you can show error messages. Python has a similar thing where the last exception is stored in the sys module. So this is not the interesting one. The interesting one comes from this one up here, and you'll notice that it's repeated a bunch of times. And that's because we called the function a bunch of times, and so we expect to see the thing repeated. This told us a few things. First, the call stack here, so you can see that get primary name function that we saw before, as well as 4 functions and then malloc below it, which if you remember from our little graph here, we had 4 unknown functions and then our malloc. And so this kind of matched for me up with the profile that I had already found, which is nice. Oh, we can't see that. Get primary name. There you go. And it tells us kind of what the object types are. In this case, it's an OS XPC connection. And so that kind of gives me what to look for. And it shows us like how it was allocated and why it didn't get freed and that sort of thing. So from there, I jumped into the code for that get primary name function, and I started hunting around for things that created the connection and ultimately didn't free them. So I hopped into the code here, this get primary name, and we have this con. This con variable is what we're going to look for. Go away, GitHub. No one likes that feature. Okay, so we find con. We create the connection here. Great, cool. If it's none, we go to cleanup, blah, 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 or null, go to cleanup, blah, blah, blah. So we should expect some cleanup down here. And if we look at our connection here, one of these things does not like the other. The cleanup code for connection just calls XPC connection cancel. And I'll spare you the details, but I look through the docs. They're not very good because they come from Apple. I look through the docs, and in some of the XPC connection creations, they tell you to use XPC release, but this one specifically did not, for whatever reason. However, it creates the same type as all the other ones, and all the other ones are freed with XPC release, and so my guess was that this connection cancel was the wrong call here, and it should instead use XPC release. So what I did from that is I built a version of krb5 that has that fix in it, and I've pre-built that into this location down here. Don't super worry about that. But if we recompile my little C code here, and I run it through leaks again, leaks at exit a.out, run it through leaks again. I gotta scroll through all this garbage. Okay. We run through leaks again. We notice that there is still a leak here, but it's only in that error message, and we don't see any other leaks. And so this tells me that I have fixed the memory leak. Oh, a bit of a whirlwind. And then I sent that patch to fix the leak, and it's already been committed. So got rid of the connection cancel, and it's now correctly using XPC release. Unfortunately, the sad part of this is an macOS specific bug, and so the memory leak in prod that I was chasing, I did not find. Instead, I found a macOS specific bug. But I still fixed it. I still learned a cool new tool, and hopefully you've learned a cool new tool too. Anyway, hopefully you found this useful. If there are additional things you would like me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.